Hello, this is Stat134, Lecture 8. Last time we covered the hypergeometric distribution, which is the analog to the binomial distribution when we draw without replacement. In other words, we have dependent trials. Just recall that the probability of a poker hand being four of a kind is an application of a generalization of the hypergeometric called the multi-variable hypergeometric formula. Now, in this case, we can first think of having the chance of our poker hand being four jacks and a king. So the chance of that is out of 52 choose 5, which are the number of poker hands. We choose out of the four jacks in our deck 4, and out of the four kings in our deck 1. So that's the highlighted part of the formula there. And now we have 13 choices for our four of a kind, and one choice for our single card. So that would give us the answer. And this we saw is completely equivalent to the formula on the right, where we're using the slot method and thinking of having an ordering of the cards. So the chance of having four jacks followed by a king, for example, is 4 over 52 times 3 over 51 times 2 over 50 times 1 over 49 times 4 over 48. Then we can remove the assumption that the four jacks are first. 5 choose 4 then is the number of different places for the four jacks in the 5 cards. And then, as before, there are 13 choices for rank instead of jack and 12 choices for rank instead of king. So today what we're going to do is a harder quiz level hypergeometric formula, and then we'll talk about some counting strategy and finish off with an approximation of the hypergeometric by the binomial. So this is a past quiz hypergeometric question. You and a friend are playing poker, and if each of you are dealt 5 cards from the same deck, what's the chance that you both get a 4 of a kind? So one way to do this is to break up into 2 steps. First, we're going to find the chance that our friend gets 4 of a kind, and then given the fact that our friend got 4 of a kind, we're going to find the chance that you get 4 of a kind. So the chance that your friend gets 4 of a kind is what we just calculated above. Now, the chance that you get 4 of a kind, you have to be a little bit careful here, because the single card you have may be the same rank as the single card, which I denote as B, from that your friend got, or it might be different. So we'll have 4 choose 4. I'll just highlight this. So we'll have 4 choose 4. And now if the single card is B, the same as your friend's single card, then there'll be 3 choose 1. Otherwise, it should be 4 choose 1, except that we'll have 10 different ranks that the single card can come from, because yes, I hope that's clear. So we can rewrite this. We can rewrite this now. First of all, we multiply these and can rewrite it as shown here. So here I'm just multiplying 12 times 4 choose 1, which is 48 choose 1 or 48, and similarly for the next. So this introduces a general counting principle, which is to try to break the problem into a sequence of steps and apply the multiplication rule. This is a very powerful principle. So to illustrate this with another example, imagine there are 3 Democrats, 2 Republicans, and 2 Independents sitting around at a table. what's the chance the Democrats sit together, the Republicans sit together, and the independents sit together? Well, I know that this is unlikely, but let's imagine that the probability is of these different political groups sitting in various places on the table is random. The way I'm going to break this problem up is I'm going to first find the chance that the Democrats sit together, and then assuming that the Democrats are sitting together, that the Republicans are sitting together, and then assuming that the independents are sitting together. So first, the Democrats sitting together, I'm going to first assume that the Democrats are the first three consecutively in the table. So the chance of that using my slot method is 3 over 7, 2 over 6, 1 over 5, and so on. Now, there are 7 positions for my first Democrat, so I can just sort of slide those 3 Democrats around the table. So I have to multiply this by 7. Now, assuming that the Democrats are seated, I'm going to place the Republicans now. Let's assume that they are just below the Democrats there. So the chance of that would be 2 out of 4, 1 out of 3, 2 over 2, 1 over 1. And there are 2 positions that the Republicans can be in only, not 3, because remember the independents have to be next to one another. So you can't have just an empty seat between the Republican and the Democrat. So similarly for the independents, actually then that's just 2 over 2, 1 over 1, and we just multiply all these together. Here's another example. In a well-shuffled deck, find the probability that Jack, Queen, Kings appear as 12 consecutive cards, and the Jacks are grouped together, the Queens are grouped together, and the Kings are grouped together. So in other words, for example, you have Jack, 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 Queen, 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 King, 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 or it could be in other orderings, but the Jacks, Queens, and Kings have to be next to one another as a group. So first, I'm going to break this problem into finding first the chance that Jack, Queen, Kings are consecutive. So for example, it might be Jack, Queen, Jack, King, King, Queen, so on. Okay, so the chance of that, so the chance of that would be, let's first assume that the consecutive cards are at the beginning of the deck. So that would be, using my slot method, that would be 12 factorial, 40 factorial over 52. Now, there was no reason to assume that they come first in the deck. So what I'm going to do is a good trick you should learn. So I'm just going to glue all of these 12 consecutive cards together and think of them just as one card. So now my 52 card deck is really 41 cards because my 12 cards are glued together. So I'm just going to multiply by 41 choose 1, which are all the ways that I can place those glued cards in different positions in my deck. Now, given that the Jack, Queen, King are consecutive, I'm going to find the chance that the Jack, Queen, King are together. So first I'm going to assume that Jacks are first, Queens are second, and then Kings are next. So there are, so it would be using the slot method 4 over 12, 3 over 11, and so on. So you can see quickly that it's 4 factorial, 4 factorial, 4 factorial over 12 factorial. And then and then there is no reason to assume that Jack, Queen, and King have to come in that order. So there are 3 factorial permutations of those. Multiply these together and you get the answer. Then we did a concept test here. So Adam, Jess, and Tom are standing in a group of 12 people. The group is randomly split into 2 lines of 6 people each. The chance that Adam, Jess, Jess and Tom are standing next to each other in one of these lines is, so the answer is B. And what I did is, following my principle, I broke it into 2 steps. First, that Adam, Jess, and Tom are in the same line, and then given that they're in the same line, that Adam, Jess, and Tom are consecutive in that line. Okay, so what's the chance that Adam, Jess, and Tom are in the same line? Well, let's first assume that Adam, Jess, and Tom are in line 1. What's the chance of that? Well, so I can think of, I have my 12 people, and I'm selecting 6 for line 1. There are 3 good people, which is, of course, Adam, Jess, and Tom, and there are 9 bad people, which is everyone else. So I'm just going to apply my hypergeometric formula, and that's the answer to that. And now there are 2 lines. It's equally likely that Adam, Jess, and Tom are in each of the 2 lines. So the addition principle applies, and I just multiplied that by 2. So now let's find, assuming that Adam, Jess, and Tom are in the same line, that they are consecutive. Well, this is similar to the previous problem. So I have the 6 people using the slot method. So I'm going to assume that Adam, Jess, and Tom are come first. Not necessarily, the order of them doesn't matter, so it could be Jess, Adam, Tom. So that'll give me 3 factorial, 3 factorial, 6 factorial, and then there's no reason to assume that they're the first in the line, so I'm going to glue them together so that now my line has 4 people in it, and 4 choose 1 is what I want to multiply by. Multiply that together, and we're good to go. So I explain this here, and finally, binomial approximation to hypergeometric. This is very easy. So binomial is drawing with replacement. Hypergeometric is drawing without replacement. Now, if your population size is very large, these are essentially the same, right? I mean, if your population size is very large, then even if you're drawing without replacement, it is essentially drawing with replacement, because the chance of you drawing the same card twice is basically nothing. So here's an example. Only 2 types of students in the class of 100. The class of 100 has 70 students getting an A and 30 students getting a B. A sample of 5 students at random without replacement, and find the probability that you get 3 A's and 2 B's. So the hypergeometric formula gives you the formula shown there. And you can think of this as binomial, in that success is that you choose an A student, and the chance of having an A student is 70 over 100. So we just apply the binomial formula. We have 5 choose 2, or 5 choose 3, I suppose, although they're the same. And that gives you an approximate answer. Next time, chapter 3. Have a wonderful day, and I will see